introduce you, Carlos.
Okay.
So good afternoon for all in this audience. It's my great pleasure to introduce you, the plenary speaker of this afternoon section, Professor Carlos Kenig, from the University of Chicago. He will deliver a talk entitled Unique Continuation for Non-Locality Specific Equations. Before starting, I would like to give you a brief introduction about Professor Carlos Kenig, our plenary speaker. Professor Carlos Kenig received his PhD from the University of Chicago in 1978. After a position as instructor at the Princeton University, he held positions at the University of Minnesota, becoming professor in 1983. In 1985, he returned to the University of Chicago as a professor. Since 1999, he has been the lowest block distinguished service professor at Chicago. Professor Kenig works in harmonic analysis and in PD in general. His recent research interests include boundary value problems under minimal regularity conditions that generate diffusions, free boundary problems, inverse problems, and nonlinear dispersive equations. In 1986 and 2002, he was an invited speaker at international congresses in Berkeley and Beijing. He has been the recipient of Sloan and Guggenheim Fellowships and of the 1984 Salem Prize. Since 2002, he has been a fellow of the American Academy of Arts and Sciences. Professor Kenig has been a member of the Scientific Advisory Board of the American Institute of Mathematics. He currently serves on the Scientific Advisory Board for the Banff International Research Solution and on the Scientific Steering Committee for the Maxwell Institute Centers for Analysis and Nonlinear PDEs in Edinburgh, Scotland. Professor Kenig serves on many editorial boards and is a past managing editor of the Journal of the American Mathematical Society. In January 2008, the American Mathematical Society awarded Professor Kenig the Boucher Prize for his important contributions to harmonic analysis, partial differential equations, and in particular to nonlinear dispersive equations. Kenig's work has been influential in the analysis of well-postnets under minimal regularity assumptions for physical equations. Thank you, Kenig, for accepting our invitation to participate in this meeting. You can.
Well, yeah, thank you very much. It's a pleasure to be virtually here today. I hope you can hear me well.
Okay. Yes, you can.
Okay. Okay, so no, I don't know what happened. So today we're going to talk about the unique continuation for nonlinear dispersive equations. The study goes back to work of So and Scherer in 1987 for the correct de Vries equation, and of Isakov in 1993 for the Schrodinger equations. The type of results that they proved was that if two solutions are sufficiently regular and agree on an open set, then an open set in space-time, then they must agree identically. Implicit in such results is the existence of such solutions, of course, and that's the result of a substantial body of works by many authors. Their works relied on Carleman estimates, which is, of course, fundamental tool in the study of unique continuation. In 2020, with Ponce and Vega, we studied corresponding results for the Benjamin-Ono equation, which is a classical dispersive equation. Here's the Benjamin-Ono equation, and a distinguishing feature is that the top order term has this non-local property because there's a Hilbert transform in front of the second derivative. So the difficulty in proving unique continuation in this case is the non-locality of the Hilbert transform, and it makes the use of Carleman estimates very non-obvious. Nevertheless, we did manage to prove that if we have two solutions to some general nonlinearity Benjamin-Ono equation, which agree on an open set, and are sufficiently regular, then the two solutions are the same. Let me skip this part. And the key observation for the Benjamin-Ono equation was the following. Suppose you have a function such that itself and its Hilbert transform vanish on an interval I. Then the only possibility is that the function is zero. And the reason for this is that if you consider the analytic function in the upper half plane, whose boundary values are f plus I times the Hilbert transform of f, so this is the boundary values of an analytic function, and the hypothesis it would vanish on an interval, and that makes it zero. In a subsequent paper with Pilot, Ponce, and Vega, we established similar results in higher dimensions for Schrodinger type equations, this time based on non-local operators, just like the Benjamin-Ono equation. So in one dimension, here are some of the models we described, and my main interest today is on dimension greater than 1. So the equations that we studied are I ddtu minus the Laplacian plus m squared raised to the power alpha over 2 plus a nonlinearity p of u bar, which we can say is a polynomial that is zero at the origin. And the fractional power we chose to be between 0 and 2. The result that we obtained in this case is that if u1 and u2 are sufficiently regular solutions of this equation, which agree on an open set in space-time, they must be equal. So let me just give a brief description of the argument in the case when u2 is 0 and u1 is u. So the assumption is that u is 0 in some open set in space-time. It verifies this equation star here, and the conclusion is that it must be 0. So how do you prove this? Well, first, since u is 0 in an open set in space-time, then the time derivative of u is 0, just by differentiation. And p of u, the nonlinearity is also 0 because u is 0. So thus we reduce ourselves to the fact that the non-local operator minus Laplacian plus m to the power alpha over 2 of u is 0 in omega, and u is 0 in omega. So this is the situation. We have a function v of x, which is 0 in some open set in Rn, and this non-local operator is 0 in the same open set. And now the surprising thing is that the non-local character helps you. And we're reduced to proving the following theorem. Suppose you have a function with some regularity that satisfies that this fractional derivative in an open set is 0, and the function itself is 0, then v is identically 0. So let me go first to the case when m, the mass, is 0. This result was due to Ghosh, Sado, and Ullman in some works on inverse problems. And they relied crucially in a previous work in the thesis of Ankana Ruland. So let me now explain the proof of this last theorem in the simplest case when alpha is 1. So what we have is the mass is 0. So what the operator that we have is the square root of minus the Laplacian. So the thing that you do in this case, you add an additional variable y and consider the elliptic extension of v, which we will call capital V of xy, which solves Laplacian in x of v plus the second derivative in y of v equals 0 in the upper half plane, Rn plus 1 plus, and at y equal to 0, v is little v. Now, with this equation, a simple calculation shows you that the square root of the Laplacian acting on v is nothing more than the y derivative of this capital V at y equal to 0. So then you are in the situation where you have a function which is harmonic in the upper half plane. It is 0 in some open set, and the y derivative is 0 in that open set, which is on the boundary of the upper half plane. And so we simply extend V to be 0 below the upper half plane. And because we had the whole Cauchy data equal to 0 nu, the resulting function is still harmonic across the boundary. And since it is 0 on an open set below the upper half plane, it must be identically 0. And so V, which is the part above, also is 0. And then the restriction of it to the boundary is identically 0. Now, the same proof works with the mass. Now, if alpha is not 1, to prove this requires considerable more work. One uses the by now well-known Caffarelli-Silvestri extension, V of xy, which now solves this degenerate equation, minus Laplacian of x of v, plus 1 minus alpha d dy over y of v, minus second derivative in y of v, v at 0 equal to little v, and one has that the alpha over 2 power of this is basically the conormal derivative of this degenerate operator, which is given by this formula. And it's a conormal derivative because this, this equation with a drift term can be written as a divergence form elliptic equation, which is degenerate elliptic, with the weight y to the 1 minus alpha. And coincidentally, in 1980, with Fabes and Serapione, we had studied precisely this class or a generalization of this class of equations. This power makes the weight what in harmonic analysis is known as an A2 weight, and we developed a whole regularity theory for this class of equations. And this is instrumental in the Caffarelli-Silvestri approach. Anyway, L alpha is a degenerate elliptic operators, and we have that under these assumptions, V equals 0 on an open set at little y equal to 0. This conormal derivative is 0 also, but it's of course a degenerate conormal derivative, depending whether alpha is bigger than 1 or less than 1 in the range between 0 and 2. And the work of Ruland shows that then Ruland worked with these degenerate equations and proved unique continuation theorems for them, and this shows that V vanishes of infinite order, and then little v has to be identically 0. Now, with Pilot, Ponce, and Vega, we adapted this to the case with mass. So the work of Ruland uses Carleman estimates for degenerate elliptic operators, like this L sub alpha. One, of course, needs to assume that some solutions exist. Otherwise, we would be talking about the empty problem. But it is not difficult to prove that solutions to this nonlinear Schrodinger equations do exist. This can be done using Fourier arguments and a simple fixed point argument in sufficiently high order Sobolev spaces. Okay, so this is the background. And I will turn now to our results, which are in a work in progress. We're at the final stages of preparation of the paper. So what we wish to do is replace this constant coefficient fractional operator with a variable coefficient version of it. So consider an elliptic operator of the form L of u equals a minus divergence form of ajk plus a zero order term c of x. The coefficients are assumed to be symmetric, elliptic. We'll assume, just for simplicity, this is not a crucial assumption, that c is bigger than or equal to lambda positive. The theory can easily be extended to c bigger than or equal to 0. And we make some regularity assumption on the coefficients that I will explain in a little while. They have sufficiently many derivatives which are bounded. But in addition, we make an asymptotic flatness assumption. We assume that the coefficients at infinity tend to a constant. But we don't impose any rate for the convergence. So And of course, without loss of generality, by using a rotation and a scaling, you can assume that A0 is the identity. Okay. So we consider this operator L, and we assign to it the minimal domain, which is the set of F in L2, such that there exist test functions Fj, which converge to F in L2, such that L of Fj also converges in L2. And that's the so-called minimal domain of L. And we then write G to be L of F. And the first thing that we prove is that L is a positive self-adjoint operator in L2, and its spectrum is contained in lambda to infinity, where lambda is the ellipticity constant, basically. So using the spectral theorem, we can consider the fractional powers of the operator L. And so we can also consider the following nonlinear Schrodinger equation, where we now use this variable coefficient fractional order elliptic operator. So the first result is that if you have a sufficiently high Sobolev space and the coefficients are sufficiently regular, then this problem is actually well posed in the Sobolev space HSN. And the second part is that if you have two solutions in the space of well-postedness, and suppose there is an open set in which they agree in space-time, then they're identical. Okay, and P is again a polynomial, like in the constant coefficient case. So let me just say a word about the second theorem. The second theorem is the unique continuation. The second theorem uses a version of the Caffarelli-Silvestre extension approach, which can then be extended to the variable coefficient case. And this was in a series of papers by Ruland, and we extended them a little bit. And this extension works, requiring quite a bit of effort, which is extremely technical, so I'm not going to discuss this here. So what I will do is return to the second theorem, which is this uniqueness theorem. And again, this uniqueness theorem reduces to a uniqueness theorem for the fractional order operator with variable coefficients. So anyway, and then we have to prove the well-posedness for this fractional order elliptic operator with variable coefficients. And this part is highly non-trivial. And in order to understand it, we have to go deeply into the functional calculus for the operator L. Okay. So the third theorem deals with the fractional calculus, and we pick some integer bigger than n/2, and this is in order to allow for the application to the well-postedness theorem. For the next two results, for instance, if alpha is between 0 and 1, we just need C2 coefficients. Okay, even C1 coefficients, actually. So the first part of the result is that all the fractional powers are unbounded positive self-adjoint operators on L2. I mean, this is just the spectral calculus. The second part is what the domain of these operators are. They are the standard Sobolev spaces, and there's comparability of norm between the fractional powers and the Sobolev norm. Okay? Once we have this theorem, it is not difficult to prove the well-posedness result. So let me just sketch this. We have a little bit of time here still. So I apply the operator to a very high power to the equation that I want to solve. And here I observe that these two operators, the fractional power and the large integer power of the operator, they are both obtained by the fractional calculus. And one of the very difficult parts of the theory is to show that when this is a positive integer, the operator defined by the functional calculus and by pure composition agree. Okay, and this is one of the theorems one has to prove, and in order to do that, I myself had to learn all the spectral theory that I hadn't learned when I was a student. And I have to say, I have to confess that that was quite a lot. And I'm a bit ashamed that I never studied this as a student, but I'm making up for it now. Okay. So now we can flip the two operators by the spectral calculus. We call this V, and now we can represent this equation in integral form using Stone's theorem, and we get that if W is this, W of t can be represented by this operator by Stone's theorem, and the inhomogeneous term can be represented by this sort of Duhamel type term. And then we use again the fractional calculus. The norm of W in L2 by definition equals this, because this is what W is. But by our theorem 3, this is comparable to the normal Sobolev norm. And the same for the initial data. And since this is a sufficiently smooth coefficient differential operator, we do the same to the nonlinearity in the Duhamel term, and the L2 norm of this is bounded by a very high power of the Sobolev norm, which depends on this nonlinearity. Now, once these inequalities are set, you can solve the integral equation by fixed point. It's an exercise. So the key point in order to prove this well-postedness result is the spectral theorem results in theorem 3. So maybe I recall what theorem 3 says. And the main point is that the domain of the powers is the corresponding normal Sobolev space, and the norms are equivalent. And then the main part of this is the proof of the equivalence of the Sobolev norm with the powers of the norm. And let me do this in the case when f is in C0 infinity, okay, which is then set in both kind of spaces. Okay. So the first step we're going to do it is in the case m equals to 1. So when m is 1, we have L, and the L2 norm of L of f can be bounded by the H2 norm of f by the smoothness assumptions on the coefficients. So the difficult part here is to prove that the H2 norm itself is controlled by L of f in L2. And it's in this part of the argument, and only here, that we require the asymptotic flatness of the coefficients. So the first thing you do is that you can bound the L2 norm of f and the L2 norm of the gradient of f in terms of the L2 norm of script L of f. And this is just ellipticity, it's just an integration by parts here. We look at LFF, we write it like this, we integrate by parts, we use the lower bound here, and then we control the L2 norm. Once we control the L2 norm, we use the ellipticity to control the H1 norm. Okay? So recall L is like this, and we were going to assume now that the A0 is the identity at infinity. And we want to show that the H2 norm is controlled by this. And recall that the H2 norm is the case when L is the Laplacian. It's basically the L2 norm plus the L2 norm of the Laplacian of f. And we need to show then, because the L2 norm we are already controlled by L of f, that the Laplacian of f in L2 is controlled by L of f in L2. And so here we do a chopping up argument. we pick a cutoff function theta, 1 on x less than 1, supported in x, 1 on x less than a half, supported on x less than 1, rescale it so that everything is up to r or r over 2, and we write our operator A as a sum of three, the matrix A as a sum of three matrices. The first one is 1 minus theta r of A minus the identity. The second one is theta r of A minus identity. And then the third is the identity. Okay, so this is completely elementary. But let's understand the various terms. The first one is the identity, the Laplacian. This is the guy we want to control. The second one is A1. And A1 has, where is A1 supported? It's supported where x is bigger than r over 2. So A1 is supported near infinity, where A is very close to the identity. So A1 is a small matrix. And A2, we cannot say anything about its size, but we know that it's compactly supported. Okay? In the ball of radius r. Okay. So I'm going to do a proof. I'm going to do various proofs. It's a bit daring, but okay. Why not? So we already have that the L2 norm is controlled by the L2 norm of L, and the gradient is controlled by the L2 norm of L. So we just look at the Laplacian. And remember, the Laplacian can be written as L minus this one minus that one. So by the triangle inequality, we get these three terms. And this is the one we like. And now we have to get rid of these two other terms. A1 is the one that comes near infinity, and that's the one that is therefore small. Now I just differentiate through, I get the gradient on A1 and the second derivatives on F. And then I just say that the L1 norm, or the L infinity norm of the gradient is just bounded by this C1 norm of the coefficients. So the term corresponding to the gradient of A1 is controlled by the gradient of F, and the gradient of F is controlled by L of F. So this is an irrelevant term. And the second term that we have is where the difference between A and the identity comes, which is A1, applied to the second derivatives. So this is a small term times the second derivatives. So I write it like that. The gradient plus a small term times, since the second derivatives and L2 are all controlled by the Laplacian in L2, I just put the Laplacian. So we get epsilon r, and this I absorb into the Laplacian on the left, which is what I'm trying to control. So we end up with the Laplacian of f bounded by L of f plus this A2 term, which are compactly supported in the ball of radius r. And now on A2, I just differentiate again. And these terms I just ignore by L infinity, and the gradient of f is controlled by the L of f. And now I have to do something with this term. And now here, I'm going to use the fact that A2 is compactly supported, and I will be using L2 Schauder estimates. So I have to use a little bit of elliptic PDE. First year elliptic PDE, you can find this in the book of Evans. So Evans says that if L is elliptic, L of f in H2 is bounded by L of f in L2 in a ball of radius r by the ball of radius 2r, and the L2 norm of f in the ball of radius 2r. Okay, this guy I like because this is what I'm going to use to control. And this controls the second derivatives, so I get these two things, and now I'm done. I got that everything controlled on the right-hand side by L of f, and the Laplacian is on the left-hand side. So So now we have, I'm sorry, I moved too fast, that in H2 we have an equivalence of norms between L of F and the H2, the normal H2 norm of F. Okay. Now we need to do this for very large M, because if you remember in my sketch of proof of the fixed point argument, we needed to go to a very high Sobolev space so that the L infinity norm is controlled by that Sobolev norm. Okay, that's why we have to go to a high power of L now. Now, there are two inequalities in this equivalence. This one, again, just comes by differentiating the coefficients. So the hard one is this one, and this is the one that we proved already in the case M is 1. So now I'm going to prove this by first proving an auxiliary lemma. My auxiliary lemma is a higher regularity version of what I proved before. That is to say that LF in a space HM can be controlled below by this HM plus 2 norm of F. And the case we proved was M equal to 0, and we're going to prove this by an inductive procedure. Okay. So we assume that we know this for some M, and now I want to prove it for M plus 1. So I first introduce this commutator term. I take any mth order derivative, I apply a constant coefficient mth order derivative, I apply it to L, and I do the commutator, and I call that P. Because it's a commutator, instead of being order m plus 2, it is order m plus 1. Okay, that's all I'm going to use. So the L2 norm of P of F is bounded by the HM plus 1 norm of F. Here I use my inductive hypothesis, and I can go to the norm of L of F in HM minus 1. And of course, this is controlled by the HM norm. Therefore, P, remember, is this difference. So I bound the first term, I bound the first term in terms of P plus the second term. The first term in terms of P plus the first term is here, and then everything is bounded by LFHM, because P was bounded by that here, and this is the HM norm of L of F. Okay. So this is the inequality that I have to keep in my head for the next slide. We also know the case m equal to 0. I can apply it to this function. The H2 norm of this is less than or equal to L of it in L2. So, and before, in the previous slide, if you forgot, I'll remind you, this is this estimate. We get, using this combination, that the H2 plus M norm is bounded by the LF norm in HM. So, and we used this, the inductive hypothesis, to get started. And the conclusion now is that H2 plus M gives me HM, and that is the inductive step. And this concludes the proof of the auxiliary lemma. Okay? So now that we have this, we're going to prove the other inequality that I truly need in order to prove my well-posedness results. And this I will prove by a simple iteration argument. I write L to the k of F as L of L to the k minus 1 of F. So by the m equals 0 case, I get this. Now I look at this, and I want to reapply the argument using this. But that's why I now use the regularity case where m is 2. And so I go to H4. And then I keep repeating it until I run out of powers. And in the end, we get the H2k norm, is bounded by the kth power norm, as desired. And with that, I conclude with even a couple minutes to spare. Thank you very much.
Okay. Nice talk, Carlos. Do you have any questions or comments to Carlos? Any questions or comments to Professor Carlos Kenig? Carlos, if you, in the original problem for Schrodinger or KDV, you consider coefficients depend on t for the temporal variable, is it possible to consider any kind of...
You can consider a similar problem. And this is our next step.
Oh, okay. Thank you very much.
We're using kind of the semi-group properties here in hiding. So that's why we're using the t-independence. So to pass to the t-dependent case is a very difficult step. But this is our next task.
Okay, very nice to know this. Do you have any other questions to Professor Kenny? This is different of what I see if there are in the audience people asking us something here.
I mean, let me see. Maybe in the chat. Let me check this out.
In the chat, no?
No, there's nothing in the chat, so that's fine.
Okay, so let's thank you again.
Thank you very much.
Thank you again.